Linear systems are often being explained as a set of equations, including x, y, z, and you are asked to find these variables. If that's how you see linear systems, actually you are missing half the story. Let's say it's a busy morning and you want to make a smoothie out of three ingredients, Greek yogurt, raspberries, and almond milk. And you want to hit a target nutrition, let's say target protein, target calories, and target sugar. How can we find the right balance of these ingredients? Actually, in math world, each of these ingredients, they're not just ingredients, they can be seen as building blocks of a linear system, or what we call it later, each of them can be seen as a vector. I am Masa Shirazi, and today in Math Inside Studio, we are going to see how this problem is related to a problem, for example, in navigating a 3D space, or finding the intersection of planes in space, and how all this together relates to linear systems. We are going to see two different perspectives of linear systems, so let's dive in. Suppose we want to make a quick smoothie and we want it to be healthy but still sweet enough to feel energized. We will use three ingredients: oat milk, Greek yogurt, and raspberries. Here, each column shows the nutrition values for 1 cup of an ingredient. Now, imagine you have a target smoothie in mind. You wanted 394 calories, 28 grams of protein, and 20 grams of sugar. Here is the question: can we choose amounts of these ingredients to hit that target? Not necessarily 1 cup each, maybe 2 cups of one ingredient, half a cup of another, and so on. Let x1, x2, and x3 be the number of cups of oat milk, Greek yogurt, and raspberries, respectively. Think of each ingredient column, as a building block. We are asking whether a weighted combination of these columns can equal the target column. For now, I'll call this the column viewpoint of a system, but we will actually define it properly later. When we choose x1 cups of oat milk, it means we multiply every nutrition value in that oat milk column by x1, and the same idea holds for yogurt and raspberries. Now, when we add the ingredients together, we are really adding nutrition row by row. What do I mean here? I mean the calories from all ingredients must add up to the target calories, the protein must add up to the target protein, and the sugar must add up to the target sugar. So what we are having here is actually three equations working together, and we need them all to be true at the same time. When we strip away the smoothie story, what remains here is actually an example of a linear system. We can consider columns as building blocks and rows as rows. As we said, this is an example of a linear system, but in general, what is a linear system? Let's zoom in on just one row, for example, the row corresponding to calories. It says a combination of variables, x1, x2, and x3 must equal the target number. That kind of rule is called a linear equation. In general, a linear equation in three variables, x1, x2, and x3, has the following form. Here, the scales a1, a2, and a3, and also the constant term b are real numbers. And more generally, a linear equation with n variables looks like this. Here, the numbers or the scales a1 up to an, they are called coefficients, and b is the constant term. So we have a weighted combination of variables. Here, the word linear means that the variables appear only to the first power. We don't have square roots of variables, and we don't have products like x1 times x2. All right, let's check a few examples here. The first example is actually linear, only we have first degree terms, so it matches the definition. But the second example is not. Here we have square root of x1, which is not first degree. If we look at the third example, we have x1 times x2, so it's a product of variables, so it is not linear. And if we look at the last example, this one is also linear. Just I want to note that here, pi and square root 2, there are real numbers, so it matches the definition. In the smoothie example, all three equations are linear, and I encourage you to pause and check them. If we put them together, they form a linear system. So in general, a linear system is a collection of linear equations in the same variables. And here you can see two examples. Pause the video and check, do they follow the rules? All right, before we talk about geometry interpretation of linear system, one word matters, and that's solution. So a solution is a choice of numbers for the variables that makes every equation true at the same time. So all rows or must be satisfied. Now let's go back to our smoothie example. A solution is a choice of numbers for x1, x2, and x3 that makes all rows to be true. Let's look at the same question again, this time using the ingredient columns. Each ingredient column is a building block, as we said. Now let's test a specific choice. For example, we can choose 2 cups of oat milk, 1 cup of Greek yogurt, and 1 cup of raspberries. It means we multiply every number in the oat milk column by 2, every number in the yogurt column by 1, and every number in the raspberries column by 1. If you look at the first row, we're adding calories with calories. In the second row, we are adding protein with protein, and in the third row, we are adding sugar with sugar. And as we see, all are satisfied. So the choice 2, 1, 1 makes every equation true at the same time. That means 2, 1, 1 is actually a solution for this linear system. In smoothie language, 2 cups of oat milk, 1 cup of Greek yogurt, and 1 cup of raspberries makes exactly the target smoothie we wanted. All right, so we briefly mentioned that we can view a linear system in two different ways, through its rows or through its columns. For now, let's zoom in on the row picture, and we start with two-dimensional space. In 2 dimensions, each equation represents a line in the plane, so solving a linear system means finding where those lines intersect. So let's look at the different possibilities. Here is our first linear system. Let's draw each equation as a line. The first equation gives us this line, and the second equation gives us another line. As we see, these two lines intersect at exactly one point, and the intersection point is 1, 2. So this linear system has one unique solution. Now, consider this system. Again, we draw both lines. These two lines have the same slope but different intercepts, so they are parallel, and we know that parallel lines never intersect. That means there is no solution for this linear system. Now, look at the third system. At first, the equations look different, but the second equation is just twice the first one, so both equations actually represent the same line. This means that every point on this line satisfies both equations. There are infinitely many solutions for this linear system. In two-dimensional space, we have seen 3 possibilities: no solution, one solution, or infinitely many solutions. And now here is the question. Can a linear system have exactly 2 solutions? Not 0, not 1, not infinitely, just 2 points. Remember that in two-dimensional space, a linear equation represents a line. Also, we know that through any 2 points, you can draw only one line. This means that if 2 lines intersect at 2 different points, they must actually be the same line. And this means that they share infinitely many points. That's why, as we just saw, there are only 3 possibilities. So a linear system in two-dimensional space cannot have exactly two solutions. But how about in three dimensions? In 3D, a linear equation doesn't give us a line anymore. It gives us a plane. So instead of lines on a flat surface, we now have planes in space. Consider the equation x plus y plus z equal to 3. The corresponding plane looks like this. Let's add a second equation and see how these planes intersect. If the second equation is x minus y plus z equal to 1, as we see, they intersect along a line. So in this case, there are infinitely many solutions, all the points on that line. Let's change the second equation to x plus y plus z equal to -1. As we see, their planes are parallel and they never intersect, so there are no solutions. And if we change the second equation into 2x plus 2y plus 2z equal to 6, both planes overlap, and in this case, every point on that plane is actually a solution. So again, infinitely many solutions. What happens when we have three equations, or more generally, a system in three dimensions? Well, each equation represents a plane as we already know. So with three equations, we are looking at three planes in space. Let's start with this plane, the same one we have already seen. Now we will add two more planes. These three planes meet at exactly one point, and that point is the only solution of the system. Let's change the situation while keeping the first plane fixed. This time, one of the new plane is parallel to the first plane, so those two never meet. Even if we add a third plane, there is still no point that lies on all three at once. So in this case, the system has no solution. Finally, let's keep the same first plane again. This time, one of the new equations actually represent the same plane. So now, we don't really have three different planes, just two distinct ones. The third plane intersects this shared plane along a line, and every point on that line satisfies all three equations. So in this case, we get infinitely many solutions. In fact, there are different ways that three planes can be arranged in a space, but no matter how they are positioned, when you look at the solution of the system, they always fall into just three categories: no solution, one solution, or infinitely many solutions. All right, so let's recap quickly what we have seen so far. For 2D and 3D, we saw that the solution lies under these three categories. In fact, in general, any linear system has either 0, 1, or infinitely many solutions. So if we go back to the question we asked at the beginning about a system having exactly two solutions, the answer is always no. That can never happen for a linear system. Let's go back to our smoothie example. Each of these equations represent a plane in three-dimensional space. Let's start with the first two planes. These two planes intersect along a line. That means that every point on this line satisfies the first two equations. Now, we add the third plane, which cuts that line at exactly one point. So out of all the points that satisfied the first two equations, only one also satisfies the third. This point is exactly the solution we already found before. And now from the row picture, we can say that this is actually the only solution, or the unique solution. All right, we briefly mentioned that we can view a linear system in two different ways: through its rows or through its columns. So far we focused on the row picture. Now let's switch the perspective to the column picture. But before we do that, we need a clearer way to organize all this information. And that's where matrices come in. A matrix is just a rectangular array of numbers, and it helps us to group all the coefficients of a system in a compact way. For example, this is a matrix that has 3 rows and 4 columns, a 3 by 4 matrix. And this one is an example of a matrix with 4 rows and 4 columns, so we call it a 4 by 4 matrix. In the smoothie example, Instead of looking at the equation one by one, we organize the coefficients into columns. And as we said before, you can think of them as building blocks of this system. We take these three columns and stack them all together into a single matrix and call that matrix the coefficient matrix. We usually denote it by A. On the right-hand side, we also have a column. This one contains the constants, and this is what we call the constant vector B. And finally, we group all the variables x1, x2, and x3 into a column vector as well. So instead of writing these separate equations, we can now write the entire system in one compact form, which is ax equal to b. This equation is telling us something very specific. We are trying to combine the columns of A to produce the vector B. Notice these columns. Each column corresponds to one variable, but instead of thinking of them as just numbers, we can think of each column as a vector. So now each column becomes a vector in space. And instead of thinking in terms of equations, we are thinking in terms of movement. Each vector gives us a direction we can move in, and we are not stuck with just the original vectors. We can scale them. For example, we can stretch them, shrink them, or even reverse their direction. So if we take a vector and multiply it by a number, it changes the length, but it stays on the same line. Now, let's take these vectors and try to combine them. Geometrically, adding vectors means placing them tip to tail. If we try a simple combination, we might not land exactly on B, so that doesn't give us a solution. But we can adjust the scalars, right? Stretch or shrink the vectors differently. And in this case, 2 times the first vector plus 1 times the second vector plus 1 times the third lands exactly on B. So the solution is exactly what we expected from before. This gives us a completely different way of thinking about linear systems, not as equations, but as building one vector from others. So let's take a moment to summarize. In our example, we saw that with the right set of scalars, we could build a target vector. And actually, this idea is the key to understanding linear systems from the column point of view. A linear combination simply means choosing weights to build a target vector. And more formally, we say that B is a linear combination of vectors v1 through vn if we can scale these vectors by numbers x1 through xn and add them all together to get vector B. So at the end of the day, solving a linear system really comes down to one question. Can we build B from the columns of A? All right, now it's your turn to try this idea. Here is a linear system. First, try to rewrite it in matrix form as Ax equal to B. Then identify the matrix A, vector X, and the vector B. Try this first on your own, and if something doesn't fully click yet, feel free to leave a comment. I'd be happy to help. In the next video, we'll learn how to actually solve linear systems using elimination, and I'll see you there.